Hello everyone, I am Mary Swarnalatha, working as an assistant professor in the Department of Electronics and Communication Engineering. In today's lecture, we are going to discuss about the statistically independent random variable concept as well as the density and distribution function of sum of two random variables and several random variables. So first we'll see statistical independence. In the previous lecture, already we have seen that if two events A and B are said to be independent if and only if the probability of the intersection of these two events is equal to the product of the probabilities of the individual events. So what is the condition for two independent events A and B? Such that the probability of the intersection of two events A intersection B is equals to the probability of the event A and the probability of the event B. So this is a condition for independent events. Now, the same concept we are applying to the random variables also. For example, if x and y are two independent random variables. So here x and y are what? Two random variables. On these random variables, I am defining two events. What is event A? The first event A is equals to here x is less than or equals to x. It means the random variable x is taking up to the value of small x. And what is b equals to y less than or equals to y. So these are the two events which have been defined on the random variable x and the random variable y. Then what is a joint event? Nothing but A intersection B. So what is A intersection B here? That is nothing but x is less than or equals to x intersection y is less than or equals to y. So it is also written as what? X less than or equals to x comma y less than or equals to y. So this x less than or equals to x and y less than or equals to y is called as what? Joint event. So it is called as a joint event. Now the probability of, if these two events A and B are independent, then what is the condition here? The probability of intersection of these two events is equal to the probability of the individual events A and B. So that is nothing but here the probability of the event. What is the intersection event here? X less than or equals to x and y less than or equals to y is equals to what? P of x less than or equals to x into P of y less than or equals to y. Now what is P of x less than or equals to x? That is nothing but what? The probability of the two random variables x less than or equals to x and y less than or equals to y is called as what? The joint distribution function. Therefore, the probability of x less than or equals to x and y less than or equals to y refers to the joint distribution function. Now, what is P of x less than or equals to x? That is called as what? The definition of the distribution function of the random variable x. Therefore, that it has been represented by what? Fx of x. And what is P of y less than or equals to y? Nothing but the probability of the random variable y takes up to the value of y. So, which is called as what? The distribution function of the random variable y. Therefore, the two random variables x and y are said to be statistically independent if the joint distribution function is equal to the product of the marginal distribution function of the random variable x and the random variable y. So, therefore, this is a condition for what? Statistically independent random variables. Now, what about the density function? We know that the density function of a random variable x is nothing but what? The differentiation of the distribution function. And similarly, the joint distribution function and the joint density function relation is what? The joint density function of two random variables x and y is equal to the what? The differentiation of the joint distribution function with respect to x and y. Therefore, by differentiating this equation 1, we are going to get the joint density function and the corresponding marginal density functions. Therefore, what can you obtain here? Fxy of x comma y is equals to what? Fx of x into Fy of y. Where what is small f represents distribution density function and capital F represents the distribution function. Therefore, the joint density function of two random variables is equal to the product of the marginal density functions of the random variable x and the random variable y if and only if the random variables x and y are independent. Therefore, these are the conditions for what? Independent random variables. Now, the same concept will apply to the conditional distribution and conditional density function also. For example, if A and B are two events, and if let us say these two events are statistically independent, then what is the conditional probability of the event A, and given the event B is equal to, what is the formula actually? P of A intersection B by P of B. For independent events, what is the condition? The probability of intersection of two events is equal to what? The product of the probabilities of two events. Therefore, what do you get here? P of A into P of B by P of B, that equals to what? P of A. Therefore, what is the conditional probability of the event A? Given the condition B equals to what? Probability of the event A only. If and only if the two events A and B are statistically independent events. Now, we just apply the same concept to the distribution, conditional distribution function and then the conditional density function also. What is the conditional distribution function of the random variable x? Fx of x by y less than or equals to y. Let us say that this is the event B. So fx of x by b equals to what? P of x less than or equals to x intersection b by p of b. So what is b here? Y less than or equals to y. So by p of y is less than or equals to y. Then what is the probability of the joint event x less than or equals to x and y less than or equals to y? That is nothing but what? The joint distribution function. That is nothing but fxy of x comma y by what is the probability of the event the random variable y takes less than or equals to y? That is nothing but what? Fy of y. So therefore, this is what? The conditional distribution function of the random variable x, and given the conditioning event has been defined on the random variable y such that the conditioning event b is equals to what? Y less than or equals to y. And then what is the condition for independence? P of A by B equals to what? P of A only. This is for what? The conditional probability equals to what? The probability of the event itself. And similarly, what is the condition for a joint distribution function if x and y are independent? We have seen if x and y are independent, then the joint distribution function is equal to what? So the condition for the joint distribution function is equals to what? Fxy of x comma y is equals to the product of the marginal distribution functions of the random variable x and the random variable y if x and y are what? Statistically independent. Therefore, for independent random variables, what is the joint distribution function of fxy of x comma y is equals to fx of x into fy of y by fy of y. So, by simplifying this, we can obtain the conditional distribution function fx of x by y less than or equals to y is equals to what? This will be get cancelled, then we'll get fx of x. It means the conditional distribution function is equal to the marginal distribution function of the random variable x itself. And in the similar manner, if I want the conditional distribution function of the random variable y and given the conditioning event has been defined in the random variable x, then what is fy of y by x less than or equals to x? That equals to what? In a similar manner, if you simplify, you'll get what? Fy of y only. And similarly, what about the density function? The distribution function is equal to what? Differentiation of the density function is equal to the differentiation of the distribution function. If x and y are independent, then conditional distribution equals to distribution function of the random variable x. And similarly, the conditional distribution function of the random variable y is equals to what? The distribution function of the random variable y itself. And by differentiating this, we'll get the conditional density function of the random variable x as well as the random variable y. Therefore, what the conditional densities are equals to the density functions of the random variable x. And similarly, the conditional density function of the random variable y is equal to what? The density function of the random variable y itself. So, these are the conditions of what? The x and y are statistically independent random variable. Therefore, If two random variables x and y are independent, then you can say that the joint distribution function is equal to the product of the marginal distribution functions. And similarly, the joint density function is equal to the product of the marginal density functions. And the conditional distribution functions are equal to the distribution functions, and the conditional density functions are equal to the density functions of the random variables itself. Now let us move to the distribution density function of sum of several random variables. So in the first case, we will take two random variables. After that, the same concept will apply for what? N random variables. Now, I am taking the first case two random variables. For example, x and y are two statistically independent random variables. So, what type of these two random variables are? They are statistically independent random variables. Now, what is the topic here? Distribution and density function of sum of random variables. So, what are the random variables here? X and y. What is sum? Is nothing but x plus y. Therefore, I have to calculate what? The distribution function of x plus y and the density function of what? X plus y. So, these two things I have to calculate in case of two random variables. Now, let us denote the sum of two random variables x and y by the symbol z. Then what is z equals to here? X plus y. So, first I'll calculate the distribution function. Therefore, what is CDF indicates here? The cumulative probability distribution function of the z, the random variable z. How we are obtaining the random variable z? The random variable z has been obtained by adding two random variables which are statistically independent x and y. Therefore, what is f z of z equals to? Nothing but from the definition of the distribution function, you can write the distribution function of z as what? The random variable z is nothing but p of z is less than or equals to z. Now, what is z here? Nothing but sum of two random variables. Therefore, substitute here. Then you will get p of x plus y is less than or equals to j. Then that equals to. So, from the properties of joint density function. So, what is that? Properties of joint density function. So, from these properties, what can you say? You can say, if you want the probability of two events such that x1 less than x less than equals to x2 and y1 less than y less than equals to y2 is equals to what? Integration x1 to x2 and y1 to y2 fxy of x comma y into dx into dy. Now here also you are having two random variables. Therefore, I take what? Double integration. And here I am representing with the symbol S. What is symbol S here? It represents the sample space such that when you add these two random variables, the sum should be always less than or equals to z. So this is a condition, or it is the limits of z. What are the limits of z here? Such that if the sum of these two random variables x and y should be what? Less than or equals to z. Therefore, into what? fxy of x comma y dx into dy. Now, what are to consider here? Consider here x and y are statistically independent. For statistically independent, already we have seen that what is the condition for statistically independent random variables? The condition is what? The joint density function fxy of x comma y is equal to the product of the marginal density functions. Therefore, what can I write fxy of x comma y as what? Fx of x into fy of y. That equals to what? Fz of nothing but the distribution function of the random variable z. What is z here? The sum of these two random variables. Now, so what is z here? My z equals to x plus y. Then what are the limits here I am going to get? What are the limits of z such that x plus y should be less than or equals to x? Z. So, what are the limits of x and y you have to consider such that when you add these two random variables, that value should be less than or equals to z. Therefore, these are the limits of x and y. Then if I, for example, if my y is from minus infinity to infinity. For example, y is from minus infinity to infinity. Then what is x equals to from minus infinity to, what the upper limit you have to take here? Z minus y. So from this, what is x equals to? Z minus y. Therefore, what are the limits of y here? Minus infinity. And what are the limits of x here? Minus infinity to z minus y. Therefore, my x1 is minus infinity. My x2 is what? Z minus y. And here my y1 is minus infinity and y2 equals to infinity. So, into what? Fx of x into fy of y dx into dy. Now, I can rewrite this equation as what? Fx of x into dx into fy of y into dy. So, that equals to, now what is this integration of minus infinity to z minus y fx of x dx. I have to substitute now. What is that? Integration minus infinity to z minus y fx of x dx. So, fx of x dx. So, what is this equation? That equals to what? Minus infinity to z minus y. What is the density function of the random variable x? There is nothing but what? The differentiation of the distribution function of the random variable x. So, since the differentiation with respect to x as well as the integration is also with respect to x, both will be get cancelled. Then you can obtain as what? Fx of x. And what are the limits of x here? From minus infinity and z minus y. Then what can you obtain here? That equals to fx of, what is the upper limit here? Z minus y. So, substitute the upper limit minus, what is the lower limit here? Fx of, in place of x, substitute the lower limit as minus infinity. So, fx of minus infinity that equals to, what is fx of minus infinity value? 0. So, from the properties of the distribution function, we can say that. Therefore, that equals to what? Fx of z minus y. Therefore, what is the integration of minus infinity to z minus y? Fx of x dx is equals to what? Fx of z minus y into what you have here? Fy of y into dy. Therefore, what is this function? So, this is nothing but what? The distribution function of, what is CDF? Nothing but cumulative probability distribution function of the random variable z. What is z here? The sum of two random variables x and y. The distribution function of sum of two random variables x and y is equals to what? Integration minus into infinity fx of z minus y into fy of y dy. Now, I have calculated what? Distribution function. Next, what I have to calculate? I have to calculate the density function of sum of two random variables. Now, how can you obtain the density function? What is the relation here? The density function of the random variable z is equals to what? The differentiation of the distribution function of the random variable z. Therefore, what is f z of z equals to? There is nothing but what? d f z of z by dz. Therefore, d by dz of, what is f z of z? The distribution function of the random variable z that equals to integration minus infinity fx of z minus y into fy of y dy. We just substitute this here. Then, after that, what do? Just interchange the differentiation and integration. Then, what can you obtain here? Integration minus infinity d by dz of fx of z minus y into fy of y dy. Now, what is the differentiation of the distribution function? That gives what? The density function. Therefore, what you get here? Fx of z minus y into fy of y dy. Therefore, what is the density function of sum of two random variables equation? Fz of z is equals to what? Integration minus infinity fx of z minus y into fy of y dy. Or else, you can write this also. Integration minus infinity fy of z minus x into fx of x dx. Also can write, because here x plus y is equals to z. So, x plus y equals to z is nothing but what is x value less than or equals to z minus y, or else you can substitute y is less than or equals to z minus x. If x is from minus infinity to infinity, and then y is from minus infinity, x is from minus infinity to z minus y. Or else you can substitute, what is that? What is one more way? If x is from minus infinity, you can substitute y is from minus infinity to z minus x. Then you will get this expression. Fy of z minus x into fx of x dx. So, by observing this equation, what is that equation? Nothing but what? It is a convolution operation. Therefore, what is fz of z is equals to what? Fx of z convolution fy of z. Therefore, the density function of sum of two random variables is equal to the convolution of density functions of the random variable x and the random variable y. Or else this how can I write down here? F y of z convolution fx of z. Because the convolution property satisfies the commutative law. That is nothing but convolution of A and B. A star B equals to what? Convolution of B and that is nothing but B star A. Therefore, what is the density function of sum of two random variables is equal to what? The convolution of the density functions of the random variables x and y. So this is done for two random variables. Now we can apply for n random variables also. For example, if I consider n random variables x1, x2, x3 and so on xn. And all these random variables are what? Statistically independent random variables. Then I'm adding all these independent random variables and then x1 plus x2 plus and so on xn. This I'm storing by new variable what? Y. What is y equals to? Transformation of x1, x2 and so on xn. What is the operation here? Just you have to add all these random variables so that you are getting a new random variable y. What is the operation performed here? This random variables addition operation. And if you want to calculate the density function of sum of all these n independent random variables, then what can happen here? Fy of y is equals to what? Fx1 of x1 into convolution. Here star represents the convolution. Fx of x2 convolution, fx of x3 convolution and so on, fx of xn. So like that, we can find out the distribution function and density function of sum of two random variables or sum of three random variables. Like that, you can obtain the sum of n random variables also. So here, we can conclude this topic as what? The density function of sum of two random variables is equals to the density function of the convolution of the density function of the independent random variables x and y. And similarly, the same concept we are applying for n random variables also. Then the density function of sum of n random variables and independent random variables, not the normal random variables, n independent random variables is equal to the convolution of the density function of these n random variables. So this is a formula to calculate the density function of sum of two random variables as well as the n random variables. Okay, let us solve one problem. Two random variables x and y have joint probability density function of fxy of x comma y is equals to k into e power minus of x plus y minus 1 when x is from 0 to infinity and y is from 0 to infinity and equals to 0 otherwise. So I should not write here equal to infinity, so less than infinity. Now, what is the first question here? Find the value of k for which the given probability density function is a valid function. So you have to find out the value of what? K. And what is the second question here? Show that the random variables x and y are statistically independent. Okay. So first what you have to do? You have to calculate the value of k. So how to find out the value of k? What is the formula there? What is the condition for a valid PDF? For a valid PDF, the condition is what? Integration minus infinity fxy of x comma y dx into dy is equals to 1. Then here in the given problem, what are the limits of x? 0 to infinity. Therefore, what are my limits of x? 0 to infinity. What are the limits of y here? 1 to infinity. So y equals to 1 to infinity. In these limits, what is the density function? K into e power minus of x plus y minus 1 dx into dy equals to 1. Now you have to solve this one. So then what can I get here? That equals to integration x equals to 0 to infinity. When you are doing with respect to y, keep y terms are constant, then k into e power minus x. So integration y equals to 1 to infinity e power. So I can write e power minus of x plus y minus 1. How can I write down here? E power minus x into e power minus y into e power 1. Therefore here e power minus x here write down. Then remaining what you have here, e power 1 is also constant, bring it outside. Then here e power minus y into dy equals to 1. So by simplifying this, We'll get the k value as what? Minus 1. Therefore, what is the first answer here? K equals to minus 1. And second bit, what do you have here? Show that x and y are statistically independent random variables. Now, what is the condition for statistically independent random variables? Just now we have seen the condition for statistically independent random variables is equal to what? The joint density function fxy of x comma y is equals to what? Fx of x into fy of y. Therefore, condition is what? Fxy of x comma y is equals to fx of x into fy of y. So, if you prove that this joint density function is equal to the product of the marginal density function, then you can say that these two are independent random variables. Now, how do you calculate the marginal density function of the random variable x? What is the formula? So, this you can see from the properties of the joint PDF. So, integration minus infinity fxy of x comma y. If you want the marginal density function of the random variable x, then you have to integrate the joint density function with respect to y over the limits minus infinity to infinity. And similarly, how can you calculate the marginal density function of the random variable y? So, minus integration minus infinity to infinity fxy of x comma y. So, this is what the marginal density function of the random variable y. If you want the marginal density function of the random variable y, you have to integrate the joint density function with respect to the variable x or the limits minus infinity to infinity. Then, if you simplify, what can you obtain here? What are the limits of y here? 1 to infinity. So, 1 to infinity. What is fxy of x comma y here? K into e power minus of x plus y minus 1 into what here? Dy. Now, what is fy of y here? Integration. So, what can you obtain here? Integration. What are the limits of x here? 0 to infinity. So, 0 to infinity. And what is the density function here? K into e power minus of x plus minus 1 into dx. So, this is what the marginal density function of the random variable y. So, by simplifying this fx of x and fy of y, then if you multiply these two, fx of x and fy of y, then you are getting, if you get fxy of x comma y equals to k into e power minus of x plus y minus 1, then you can say that these two are independent random variables. So, if you simplify, what can you obtain here? So, k into, you are doing with respect to y. So, the x terms will get constant. Then, k into e power minus x into and e power plus 1. Because you can write e power minus of x plus y minus 1 as what? E power minus x into e power minus y into e power 1. Since the integration with respect to y, so bring the terms k, e power minus x and e power 1 outside. Then what do you get here? Integration 1 to infinity e power minus y dy. Then what can you obtain here? So, k into e power minus x e into integration of e power minus y is what? E power minus y by minus 1. And the limits are 1 to infinity. So, if you substitute the upper limit and lower limit and then if you do it, then what is your density function of the random variable x is equals to k into e power minus x into e into, what is the upper limit here? E power minus infinity. What is e power minus infinity value? 0. So, minus of minus will get here plus. So, e power minus 1. So, e power 1 and e power minus will get cancelled. Then what will get here? K into e power minus x. Now, what is fy of y here? So, fy of y is equals to what? You have to integrate with respect to which variable? X. Therefore, the y terms are constant here. Then what can here? K into e power minus y and e power 1 is constant. This is from 0 to infinity e power minus x dx. Now, if you simplify, what can you obtain here? So, you can obtain as fy of y is equals to k into e power minus y into e power 1 into integration of e power minus x is what? E power minus x by minus 1. And what are the limits of x here? From 0 to infinity. Now, substitute the upper and lower limit. Then what can you obtain here? You can obtain as what? K into e power minus 1 into e power 1 into, then what is the limit of x here? E power minus infinity. E power minus infinity is what? 0. So minus of e power 0. What is e power 0? Is nothing but 1. Then what can you obtain here? K into e power minus 1 into e. Now what is k value here? Previously I written k equals to, we got minus 1. Therefore substitute k equals to minus 1. Then what is fx of x? Substitute k equals to minus 1. Then what is fx of x equals to minus of e power minus x. Then what is fy of y is equals to, what is k value here? Minus 1. Then you'll get minus e power minus 1 into e power. So e is nothing but what? E power 1 only. Now multiply these two, then what can you obtain here? Fx of x into fy of y is equals to what? E power. And here if you take common minus, then what can you obtain here? X plus y minus 1. So what is k value here? K equals to minus 1. So like that here k into e power minus x into e power minus infinity is 0. So minus of e power minus 1. So you are getting here minus. So minus e power minus 1. So you are getting here minus. So therefore here you will get fx of x equals to minus of minus will get plus. So therefore you are getting here minus 1. So what is k value here? Minus 1. Then nothing but fxy of x comma y is equals to what? K is minus 1 here. Then minus of e power x plus minus 1. Since fxy of x comma y is equal to the fx of x into fy of y, you can say that these two random variables are statistically independent random variables. Therefore, what is the condition for statistically independent random variables? The joint density function fxy of x comma y is equal to the product of the marginal density function. Then you can say that they are statistically independent. Therefore, in today's lecture, we have seen that the statistical independence of two random variables and several random variables. After that, we have seen the distribution function and density function of sum of several independent random variables. First, we have taken for two random variables case. After that, we have played for n random variable case. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.